Excellent. May not be a bad idea, but it, maybe, yeah. Thanks. Oh, this is the one Chief got. Nice.
That's on the board. Yeah.
Great.
Oh, okay. That would make sense. No, yeah. I just thought it was like a pretty. No, that makes sense.
When to start? Now, 5 minutes. 3 minutes. Okay. It's a Sunday. My gosh. Sorry? No, 55 minutes. So it's 60 slides, okay? 60. So it's a slide a minute.
I know that SIGMusic does it for an hour.
Yeah,
SIGMusic is a thing. Oh yeah. Why don't we brute force all of the portals for Siebel? Like, why not? No, just why not?
We should do that.
Like, if there are 2 portals for booking rooms on Siebel, or like 3 or 4, I mean, why is it that somebody can book the room if it's already reserved, right?
In this case, so
In
yeah,
this particular case, yeah, but
in this particular case,
Yeah,
it
Thomas,
was-
sure, but in general, it happens too, right? So I was
in
thinking,
general, it happens. Last time it happened, that was taken care of by Symmetric because they misunderstood that they had room.
I see.
So, in theory, we
You know what we need to do? We need to just start sitting and doing homework on Thursdays in that room from.
just like think about it.
Yeah, yeah.
Yeah.
Definitely.
What's up, Aditya? Yeah, no, you're right. We're still working through some stuff, but we'll get it figured out.
We should, we should.
Let me go ahead and break those 2 challenges we talked about.
Yeah, sure. I mean,
category already.
all right, great. The description is kind of what I sent you. Almost exactly, actually. So, yeah.
That cannot be good.
Something's gonna explode, bro.
Don't touch it here, so this is fine.
Yeah.
Laptop's not getting soft.
Did you ever study physics, bro?
No, like I say physics.
You did Mechie, so I assume maybe a semester.
No.
No?
My only
Ew, bro. Engineer.
That's my extent of engineering knowledge.
I almost failed engineering
I did
100.
too on purpose.
Oh, you failed it?
Almost.
Almost,
I knew
yeah.
exactly what I need to get is 50.
I see. Wait, 50 was a passing?
Yeah.
Bro, our passing was 70. That is such a high standard for engineering 100.
Well, yeah, because they want you to actually show up.
Yeah,
Because they know
I went twice in the whole semester.
Oh, I went more often, but I just like would mute my Zoom call.
You had it online, bro. You don't know how bad engineering 100 is. Oh.
I had it in alt cal. It was awful.
Okay, we should get started.
Yeah. All right. Hi, everyone. Thanks for coming Sunday. There are 60 slides. We're trying to do 1 slide a minute, but feel free to interrupt me and ask questions because each slide is probably going to take around 20 seconds. Point I'm trying to make is you'll be here for a while. Next slide. I believe you. All right, so these are the sections, keep going. Right, so why are we doing this in the first place? An introduction to cryptography, the math you need for cryptography. So generally when we run crypto meetings, I notice we throw a lot of math symbols at the audience and everyone's like, well, what do these actually mean, right? And there's no way to understand cryptography without understanding what those symbols mean. Also, Hussein gave a presentation a couple of weeks ago where everybody zoned out. So, and in it, I mean, I feel like it was an amazing presentation, okay? But I feel like it'll be more useful through the lens of a little bit more knowledge about what kind of math he was talking about. And finally, this is what happens during crypto CTFs. So yeah, next slide. What it isn't, it's not very challenge heavy because it's pretty theoretical. We will have a couple of challenges up. These challenges are more like you're going to write a program and then you're going to show me. And the challenges are going to be here, implement RSA or implement RSA in a certain way. And then I'll take a look at it. If it's working, you'll get the flag. It's not going to be super interesting for people who already know the math or crypto. So sorry, crypto folks. Next. Yeah, by the end, hopefully you all won't be scared of crypto and you'll have a better understanding of how numbers can work together to create systems that are secure information-wise. Next. All right, quick note on notation. Okay, that N and that Z, that font is called Blackboard Bold. And that N means the natural numbers 1 to infinity. Z is the integers from -infinity to +infinity. No fractions for today. Okay, yes. Zero, for our purposes, is not a natural number. Okay, right, so here's some motivation, okay? I want you all to think about this problem. This was asked to a friend of ours in, well, actually Sam, during an interview, and he didn't get the answer, but it's an interesting problem. So here's what you do. I'll give you a number, like 65536, add up its digits, you'll get 25. Add up the digits of 25, and then you'll get 7. And I want you to write a function, a program, whatever, that takes in some sort of integer, okay? And you need to give me back that single digit you get at the end of all of these operations. Obviously, there's a naive way to do it, right? You have to convert it to a string or whatever, add the digits, or you can like do mod 10 every time, add the digits, and then get 7. But that's brute forcey. Is there a cleaner way to do it? The answer is yes. Okay, next slide. This is how you do it. You can ignore the math if you want to. These two are equivalent exactly, the code and the math, okay? You take it mod 9. There's one edge case. That's what it is. Why does this work? Well, next slide. We're going to find out, okay? And why it works is interesting, right? Why should it be that you can take a number, mod something, and then solve a problem of that description? Does anybody have any intuition about this? Anyone who has not already seen this problem?
I have a question.
Yes.
What does mod mean?
Okay, we'll get to that also, right? For this specific example, I assumed you knew what mod meant, right? Oops. Any intuition, anybody, about this one? That's fine. I doubt I'll need it. Okay, so let's move on. Some very simple basics, okay? This is the operation divide. It's the vertical bar. 5 divides 25 because 5 times 5 is 25. 6 divides 54 because 6 times 9 is 54. 7 does not divide 15 because you'll get a remainder of 1. Any questions? Okay, hope not. Next. Quick true or false. Does 25 divide 125? Yes. Does 45 divide 900? It does. Does 3 divide 4? No. Does 37 divide 111? It does. Does 7 divide 1001? It does. 11 also divides 1001. So numbers can be weird. Next. Okay, what's the greatest common divider? Well, what the concept we stated before, where 5 divides 25, or 7 divides 49, or whatever. 7 is called a divisor or a factor of 49. All right. So for a number, you can list all of its divisors, every other number that divides this number. If you have 2 numbers, you list all their divisors, and then you find the biggest among those lists. That's the greatest common divisor. So here's an example, right? Here's 54 and 36. I've listed all of their divisors, right? Well, the positive ones. I didn't list negative divisors because the greatest is going to be among the positive ones. Positive numbers are bigger than negative ones. And you have to find the biggest common element in these 2 lists, right? Quick question before I show you the solution, right? The first part we already kind of discussed during Hussain's meeting. How do you find the divisors of a number? As a quick programming problem, if I gave you 2 unsorted arrays, how would you find the common maximum element? That sounds a lot like an interview question. Next slide. The way you do it is you hash one of them, or well, you put in a hash table. and then you take the second array, and then you keep checking, right? So next slide. That's the exact description if you're interested, but it should already seem to you that this is not a very efficient way of finding the greatest common divisor. Why not? Well, the most inefficient part is finding the divisors of a number in the first place, right? Husnain talked a lot about this 2 weeks ago, but factoring numbers is hard, bottom line, right? Also, the second part can get tough if the list of divisors is really, really long, which it is in the case of certain numbers. Finding the common maximum among two such lists is a pain. You might have to sort them, you might have to do weird stuff. So how do you find the GCD in an efficient way, right? Next slide. Euclidean algorithm. This is amazing. Okay, lots of people learn this algorithm in like middle school or whatever, and then you never think about it again. But I want to emphasize just how unintuitive it is to think of an algorithm like this. The way I describe GCD to you, I don't think many of us would have thought that, you know, you can solve this problem this way. Okay, so don't worry about this description. Go to the next slide. This is how you do it. Okay, you take 54 and then you use the division algorithm on 54, which just means do long division on 54, right? 54 is 36 times 1 plus 18, and then you do it with 36 and 18, right? So whatever remainder you get, you do it with that, and then the smaller of the two numbers you started with. Okay, 36 happens to be, I'm sorry, that should be 18 times 2 plus 0. Okay, next. That's it. The last remainder that gave, well, or whichever divisor gave you a remainder of 0, that's the GCD. Why does it work? Don't worry about it. There's a proof. It's not super interesting. The point is, it's insanely efficient. Next slide, right? These are that's the upper bound. It's O log B, which means it's linear in the digits of B, right? Or linear in the digits of the smaller number. It's very interesting that you can find GCDs like this, and it's very useful. I just want you to remember the definition of a GCD and that it's super efficient to compute it by dividing the numbers with each other. Okay, next slide. All right, so now you know two concepts, right? You know divides and you know GCD. All right, just with these two, we'll move on to far more interesting structures that are related to cryptography. Next slide. Okay, interesting question. What are integers really made of? Well, integers are made of other integers. You multiply two integers, you get another. And these integers themselves are made up of other integers. You keep doing this, right? And what do you get? Eventually, next slide, you reach integers that you can't split up anymore. And these integers are the primes. So in a sense, all the other integers are made up of primes. And this itself should somehow tell you that, you know, primes are interesting, because if you can somehow understand the primes, you understand interesting properties about other numbers as well. Okay, next slide. This is an interesting theorem. What it basically says is what we discussed, that every single number can be expressed as a product of prime powers or primes raised to certain powers, right? Next slide. So by the way, those pies and all look scary, right? Those product things. I had a bit of, I mean, I started to understand them when I started looking at them as for loops. So that's an aside. Those things are really just for loops. So you keep multiplying I squared in a loop all the way up until the upper limit. And same for sigmas, they're for loops with addition. Next slide. Okay, what's coprimality? If the greatest common divisor is 1, okay? So our interesting question, are all primes co-prime to each other? Yeah, all primes are co-prime to each other because prime numbers are only divisible by themselves. So 7 divides 7, and then 1 divides 7. But no other number divides 7. So, well, anyway, 5 and 8 are co-prime, 4 and 16 are not, because the greatest common divisor is 4. Okay, next. Modularity. Remember that thing we wrote? 54 is 36 times 1 plus 18. This is another way to write it. And you have to understand both those notations are exactly the same. There is no difference between these two, okay? That 54 is 36 times 1 plus 18, or that 54 and 18 mod 30, 54 is equivalent to 18 mod 36. That's how we read it. These mean the same thing. That means if you take 54 divided by 36, the remainder you get is 18. Remember, no fractions, okay? Like we said at the beginning, we're not looking at fractions. We're looking at remainders here, okay? Next. In general, these two mean the same thing, okay? that A is equivalent to B mod M is the same thing as M divides A minus B. These are two ways of writing the same thing, all right? That's a small proof up there, but it should kind of be obvious to you, or you can just quickly read that, okay? If A minus B, if M divides A minus B, that means M times something is A minus B. If M times something is A minus B, well, you take the B to the other side. K times M plus B is A. And then from our definition, if you look back at 54 times, 54 is equal to whatever, it's the same thing, okay? Next. All right, quick question, what's 16 mod 4? And I want you to give me answers from like, if it's mod 4, then the answers I want are from like 0, 1, 2, 3, right? Because remainders, the biggest remainder you can have is going to be, well, M minus 1. 16 mod 4 is 0, 77 mod 10 is 7, and you can do the rest if you want to. We don't have to. Next. Okay, any questions about mod before we move on to answering this question? No, excellent. So mod is something that you use in programming all the time too. It's the percent operator in Python and most C-like languages. Okay, so let's go back to our question about that sum of digits, right? Why does that work? Well, does everybody know we work in base 10? If you don't, we do. Base 10 numbers are represented like this. So, you know, when you do that thing where you figure out there's a place value and then there's a face value, if you ever did that. The place value is 10 raised to some power. Like if you have something in the thousands digit, it's 10 raised to 3 times that digit, right? You add all of those up, you get the number. This is a way to write that. Hopefully that's visible. Can you all see it, by the way, Dan? You can? Okay, excellent. So 10 raised to k minus 1 times the the k minus 1th digit of n, right? And so on all the way till the 0th digit of n. I start counting from 0, sorry. Next. Okay, so take the whole thing mod 9, okay? According to our solution. What do we get? Take the whole thing mod 9. Well, it's a bit hard to see what happens if you take that whole expression mod 9. So let's only look at one term of that expression, okay? So the first observation is we can take each term mod 9 separately. This is how modular congruences work. Don't worry about it. It's how they work. There's a proof. It's pretty boring, okay? You can take each term mod 9 separately. Okay, so you can take all of those 10s multiplied together, k minus 1 times mod 9 separately. And finally, there's a k minus 1 a digit of n. Let's ignore that. What is 10 mod 9? Quick. 1. Excellent. So that means all of those 10s become 1s. Another observation, if you have lots of things multiplied together, you can take them all modded separately and then shove them back in. So that's a bunch of 1s times some digit, right? What's a bunch of 1s times anything? It's just that thing. Next slide. You do that for the whole thing, right? Then what do you get? Well, you get the sum of the digits of n. So if you take a number mod 9, you get the sum of its digits, right? It's interesting. It's a strange property, and in fact, it can be generalized. If you have a number in any base, right? Obviously, there are some edge cases, but any base, I think, larger than 2 or something. If you want to find the sum of its digits in that base, you take it mod the base minus 1, okay? It's very useful that we can manipulate like congruences like that, that we can say, well, take all the 10s and take them, you know, turn them into 1s, but then don't do anything to the k minus 1 a digit of n, right? It's nice. So remember that, okay? Playing with this modular stuff is a lot like playing with equations in general. Linear congruences. I just said equations, and mathematicians like equations. You can form an equation using that weird equals to sign. Nobody says you can't. 16 times some x is congruent to 8 mod 24, okay? In general, ax is equal to b mod 24. Sorry, that should be an equivalent sign, not equal to, common mistake. Next, we're not going to worry about how to solve them. I just want you to understand 2 things about such an equation, okay? First, if d does not divide, first we take the GCD of a and m. So we take the GCD of the coefficient of that variable, okay? And m, which is, well, the modulus, right? Whatever that is, okay, you call it d. Now, if that d divides b, then there are solutions. If that d does not divide b, there are no solutions, okay? I'll give you an example, don't worry. And if d divides b, there are exactly d solutions. So here's what we're doing, okay? First, this is a way of just looking at some sort of modular equation, or well, it's called a linear congruence, right? And being like, well, does it have solutions, right? And second of all, if it does, how many, right? Next. Okay, so that's fine. We are only going to consider one special kind of congruence, okay? And this is this one. AX is equivalent to 1 mod M, okay? Now, going back to what we were talking about how to count solutions and all of that. First of all, does this have a solution? Well, if and only if the GCD of A and M divides 1, which is the only number, integer, that divides 1. It's just 1. So that means the GCD for this equation, the GCD of A and M has to be 1. What does that also mean? It means A and M are co-prime, right? That's the easiest way to say it, right? And how many solutions are there? Well, the GCD is 1, so there's exactly one solution, right? There's one solution, and for that one solution to exist, A and M have to be co-prime. Clear? Any questions? No. Okay. Next. Right. This says exactly what we discussed. This is alternate notation for that. And what X is called the multiplicative modular inverse. Every time someone says modular inverse, they mean multiplicative modular inverse. It means if in that base you take the first number multiplied by the second, you get 1. This is exactly like a multiplicative inverse in normal math. What's the multiplicative inverse of 5? It's 1 by 5. So the same relation that 5 and 1 by 5 have, A and X have over here. Okay, next. All right, here are some examples, right? What's the modular inverse of 5 mod 7? You can write it like that in Python, right? You do power 5 minus 1, 7. But be careful. It only exists if A and M are co-prime. For instance, in that case, 4, 8, whatever, Python is going to give you a value error. It says, well, I can't invert this, right? Because according to the rules of math, there are no solutions, so it's not invertible. So always be careful about, modular inverses and A and M being co-prime. Next. Okay. Whew. So we've discussed a bunch of things. Any questions up till now? Because this is where it's going to get slightly harder. Okay, so make sure you at least roughly understand most of what we've been talking about. Any questions? Yeah.
Is it computationally hard to find that inverse?
The modular inverse? No, in fact, you can find it using the Euclidean algorithm, so it has the same complexity. Any others? No, okay, great. All right, oops. So systems of equations are also objects that we study sometimes. Well, if we had one equation, you can have 3 equations together, and then you want a solution to all of them, and X that satisfies all of these equations. And this was studied a lot by ancient cultures. I mean, they were fascinated by this kind of equation. There's a counting puzzle up there. You can read it if you want. But in general, this is a very interesting problem to solve. And the Chinese remainder theorem is a way to solve this kind of problem. It's actually an algorithm, not a theorem. Okay. The actual solution to this is X is equal to 23, or well, that's one specific solution. There's a whole class of solutions, 105K plus 23. All right, next slide. We're only going to study one specific case of the Chinese remainder theorem, or one form, which is that of 2 simultaneous equations, right? And we're not even going to study how to solve it. I don't even want you to worry about that, okay? All I want you to care about is the fact that for the Chinese remainder theorem to solve this, or for there to be a solution, you want P and Q to be co-prime, okay? And the Chinese remainder theorem states that this eventual solution you get, right? Or if you get 2 or 3 solutions or whatever, you get a whole class of solutions. All of them are congruent to each other, modulo PQ, okay? That's it. P and Q are co-prime, and then all the solutions you get are congruent to each other, mod PQ. Next slide. Okay, this is all we care about. Make sure you understand what's on this slide. Next. All right, now next slide. Okay, we're going to slow down a bit here. Okay, this is what Fermat's little theorem states. It states that if A and P are co-prime, all right, A to the P minus 1 is 1 mod P, and P is prime. Okay, Fermat's little theorem states that this is always true. Why is this always true is what we're going to examine. We're going to use something called the method of necklaces. Necklaces are a specific kind of mathematical object, and they've defined another kind of object called bracelets. And I spent a lot of time over the past few days being like, what's the difference? It's not too interesting, but what we're going to look at it as next is a circular linked list. That's what a necklace is. Okay, so we're defining 3 things right now. Okay, an alphabet, a string, and a necklace. All right. What's an alphabet? It's a bunch of symbols. Okay. 1, 2, 3, 4, 5. That's an alphabet. 0, 1. That's an alphabet. C, D. That's an alphabet. Right. Weird Greek letters together. They form an alphabet. Right. A string is a bunch of symbols together. Right. So alphabets can generate strings. All right. So if I have the alphabet A, B, well, if I have our English alphabet, right, A to Z, they can generate all sorts of strings. In fact, every word is a string that's a part of that alphabet, assuming you don't use any symbols outside that alphabet. Finally, a necklace. Now, this is interesting. A necklace is literally a circular linked list. You should understand that those three things in red are exactly the same necklace, but they're different strings. Clear? So we can take SIGPwny, rotate it by 1. So then the Y goes there, right? And you have to understand, it's the same necklace. We're just looking at it in different ways. I'm writing it in different ways because, well, the board is 1D, right? It's the same object, all right? Be very careful about these definitions because they will count, okay? Next. All right, here's an example, okay? Here's an alphabet. The symbols used in this alphabet are A and B, okay? The alphabet has 2 symbols, so we set a variable A to 2, okay? That's a count of the number of symbols in the alphabet. P is the length of the strings in this alphabet, all right? So the maximum and only, so all the strings have to be exactly 5 letters long, 5 symbols long, whatever, okay? So you can verify for yourself that I've written down all possible strings in this alphabet. I have a question. How many are up there? Don't count them. It's just going to be 2 raised to 5. It's going to be A raised to P in general, okay? Next slide. Okay, A raised to P in general. Now, here's the question that we're going to ask, okay? If you have a set of strings defined by A and P, just like we did before, we have that whole set of strings, right? And so the question is, how many necklaces are there that have at least 1 symbol? So go back, okay? At least 2 different symbols means that you don't count B, 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 and A, or whatever. We don't care about those, okay? How many necklaces do the rest of them form, right? We already established that more than 1 string can correspond to 1 necklace, right? We know that. But then how many necklaces do all the strings except the repeated symbol string correspond to? That's what we're going to aim to answer. Does anybody have any questions about the question we're asking? Is the question clear and well-defined? Okay, next. And we're given some additional information about P being prime and A and P being co-prime. All right, great, whatever. Next. All right, so let's examine how, strings and necklaces interact with each other, right? We're just trying to gain some intuition here about, well, what can we do with these 2 objects and how do they talk to each other, right? Here's a string. It's not from our alphabet, okay? It's a random string, right? And I'm looking at, well, how many strings correspond to the same necklace? So you can tell that ABB, 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 ABB. That's the necklace. That's the string, right? Rotated by 1, that's another string that's the same necklace. Rotated by 1 again, that's another string that's the same necklace. Rotated by 1 again, well, we've got the same string again. So there are only 3 ways to represent this necklace as a string. Clear? Why? Well, because there's that repeating ABB, ABB in there, right? So it's that ABB is a length of 3, right? And my whole string has a length of 12. 3 divides 12. So that thing is going to repeat itself over and over and over every time I rotate the string by 3. Clear? Don't have any problems with that, right? Okay. Any questions, ask, because this is very, very important to the proof, okay? It should be clear to you that, okay, another question now. If I have, let's say, I give you 2 random numbers, right? If I give you a string of length 14, right? Or sorry, if I give you a necklace of length 14, can you tell me for sure how many strings it'll have? No, you can't, because I haven't told you what that necklace is made of. If for some reason there's a repeating pattern in there, well, then you don't know, right? Next slide. Well, this is what we just observed, but what if there isn't a repeating pattern? Okay, then it's fine. The problem is we generate the whole alphabet. So there will always be some combination that has some repeating pattern that's going to trip us up, right? So if the string is of length 14, as soon as one of those permutations will have or well, some of those permutations will have a repeating segment of 7, right? And then, well, we've messed up, right? Next. Here's the thing. We know that our length is a prime. What does this tell us about repeating periods, right? That means the only numbers that are going to properly divide our length to create a quote unquote repeating segment are 1 and the length itself. So repeating segment that is of the length of the whole string or necklace doesn't actually repeat, right? Because it's the string itself. And if it's of length 1, we'll look at that case, right? So next, case T is 1. Well, it's simple, right? If the repeating period is of length 1, then we just get A 5 times or B 5 times. Yes? The other possibility, next. Oh, by the way, sorry, go back. I missed something. How many cases are there like this? I'm counting cases. In a whole alphabet, how many cases are going to be one symbol repeated over and over? Exactly the number of symbols, right? If I have the symbols A, B, C, D, there's going to be a string full of A's, a string full of B's, a string full of D's, and a string full of D's. That's exactly 4 strings, right? And 4 necklaces. So there are exactly A such cases, right? So there are exactly A strings that have that repeated. What's our other case? T is P. Our period is the length itself, right? So if the period is the length, well, how many cases are these? Remember, the whole alphabet is A to the P. So remove the cases that are, well, one thing repeated, right? And that's A to the P minus A. Clear? Great. Each necklace is represented by exactly P strings. Why is that? Go back, Anakin, to the slide where you had ABB, ABB. Further back. Perfect, right here. Here, why did we have exactly 3 strings that corresponded to that necklace? Well, because if you rotate it 3 times, you get back to the same string, right? But so you have to understand that whatever the period is, T, what we're calling, right? That is the number of strings that you're going to get, right? So if the period is P, how many strings are you going to get? Go all the way forward, please. One more. Right, it's going to be exactly P strings, right? So A raised to P minus A, that removes all the strings that are of the case T is 1. So for the strings where the period is P, right? Well, they're going to be exactly P strings corresponding to each necklace, right? So how many necklaces are there? This many. Each necklace is represented by P strings. So how many necklaces are there that do not have just one symbol repeated over and over? It's this. It's going to be A to the P, that's the whole alphabet. Remove all the ones that are exactly one symbol long. That's A of them, right? And now you have some set of strings, right? And then you just divide that by P. That's the number of necklaces you have of the question that we asked. How many necklaces of at least 2 symbols? Clear? Okay, why is this interesting? Why did I talk about Fermat's little theorem and then talk about like strings and rotating them and doing weird things? Next slide. If you look at this carefully, here's the thing. The number of strings is going to be integral, right? We can't have half a necklace. Half a necklace has no meaning, right? That means A to the P minus A divided by P is an integer. In fact, it's a natural number, right? Because it's a natural number and it's a prime, right? That means that by the definition of modular congruence, P divides A to the P minus A. It divides it correctly, right? Correctly in the sense you'll get some sort of integer value, right? That means, remember what we said about modularity. If M divides A minus B, what can we also write? We can also write A to the P is congruent to A mod P. Get rid of an A on both sides. And the reason you can do that, always be careful when you're dividing modular congruences. The reason you can do that is A and P are coprime. Don't worry about it for now. Assume you can cancel A from both sides. You get exactly what Fermat's little theorem states. A to the P minus 1 is 1 mod P. Okay, we're done. Any questions about this proof? It takes some time to wrap your head around because we're juggling multiple objects and looking at them in different ways and counting them differently. Any questions? Yeah.
Might be a dumb question, but like if you slide back, you said the formula was A to the P minus A. I get that part, but why are we dividing by P?
Excellent question. The reason we're dividing by P is because each necklace is represented by exactly P strings. So A to the P minus A is a bunch of strings from the alphabet, right?
Yeah.
Right. Each necklace that has period P is represented by P strings, right? So you just divide it to get the number of necklaces. Any other questions? No? Okay, good. We can move on. Here's a manual verification. Okay. So there I've removed the two strings that we don't care about because they're made of just one repeating symbol. Above, we have the interesting ones. And if you look at those lines horizontally, each horizontal line is the same necklace. Okay. So you can verify that. Just rotate it in your head a little bit. And you'll see that 4 A's with the B at the end is the same as rotating it left and then getting the B there. Rotating it left again. You keep rotating left. It's a visual way to look at it. Okay. Great. Next slide. Okay, we're at RSA. Wow, that was quick. Next slide. Okay, public key cryptography. How many people have never heard of, or how many people have heard of public key cryptography before? Just heard of it. Okay, great. How many of you like really understand what it is and why we do it? Kind of. Okay, great. How many of you understand at a very deep level how it works? That's the problem. It's kind of hard to understand, right? But we'll take a look, right? Here's what it is. In this case, leave this image up. We'll look at it for a while, okay? Alice wants to send Bob a message, which in this image is that gem, okay? Alice wants to send it to Bob, but she can't just send it, right? Alice and Bob are separated by this barrier where attackers loom. And you can think of this as a public insecure communication channel like the internet, right? It's just a place where attackers are lurking and Alice can't just throw the gem out there and trust somebody to deliver it to Bob because they'll steal it, right? So here's what Bob does, okay? Bob's kind of smart. He says, I'm going to give you a box and a lock, okay? And this is one of those locks that you can just click shut. You don't need a key to lock this box, okay? And I'm going to send it to you. And what you do is you take the box, open it, and I'm going to send you the lock unlocked, right? And what you do is you take the box, open it, put the gem in, close the box, click the lock shut, and then send me the box. And then Bob gets the box, and only he has the key to that lock. So he unlocks it, and then he pulls out the gem, and everything is right and happy with the world. Look at it from an attacker's point of view. What did you see being transmitted? You saw Bob sending Alice an empty box and an open lock. Doesn't mean anything. And then you saw Alice sending back a locked box. And we assume that you can't unlock a locked box, okay? That's a bad assumption, but we're assuming that here, okay? What do you do as an attacker? You can't do anything, right? Because all you saw was an open box and now a locked box, right? So, well, you can't do much, right? One thing I do want you to note over here that is important is the fact that we are assuming that, and this I mentioned earlier, if you have a locked box, you can't unlock it. The only way you can unlock it is with the key. Okay. How do you create a system that corresponds to this? Okay, first of all, any questions about a system like this? Can you see any insecurities with it? Are there any questions? Yeah.
Are we still assuming that they can't solve all blocks?
Sorry?
Are we assuming that the attacker can't swap blocks?
The attacker can, well, to swap blocks, the attacker would have to take out the original lock, right? So
As they said it the first time, unlock.
that is a good question, and that's called a man-in-the-middle attack, and that is true, right? So that's an interesting point, and the way we prevent that is by using signatures, right? So if you're getting an open lock from Bob, there's a way for Bob to sign that and say, well, that's my lock, right? So yeah, that is a good question. All right, next. Here's how we build the system mathematically, okay? And this is where most people kind of get, uh-oh, but it's fine. It's not that hard. This is a very simple and very elegant system, okay? I'm not going to describe how to build the system. First, I'm going to describe how to use the system, okay? Building the system is kind of easy, okay? Once you know how to use it. Here's what it is, okay? Bob's public key is the open lock. Public key is, in my opinion, honestly, a really bad name for a thing like this. It's not a good name, okay? It's actually an open lock, okay? And the public key is just a pair of two values, a tuple, a pair, whatever, n comma e. So whatever, right? Alice gets two values from Bob, and she wants to send Bob the message m. She computes that value. She computes m raised to e mod n. And you can convince yourself that that formula thing is only made up of the three values that Alice had, her own message m, and what Bob gave her, e and n, right? Then she sends Bob whatever value that function gives her. Okay, Bob takes it, he raises it to the power D, which is his private key, which is, the key that can unlock that lock, right? And he gets the message, right? Very simple scheme. Any questions about this? Take it on faith for now that those functions are like a lock-unlock pair, okay? We'll prove that very quickly. But any questions about the functions themselves? I know I haven't told you about modular exponentiation. It's just multiplying m e times, all right? And c to the d is multiplying c d times, right? We kind of did that when we took 10 raised to the power k minus 1 mod 9, if you remember that, right? Yeah.
How does Bob get D? What is D?
That's key generation. We'll get there. For now, we're assuming the system's already in place, right? So next. All right, how do we build the system? This is a harder problem, okay? Here's how you do it. You get two primes. Ideally, you want these to be large, P and Q, and then you multiply them to get N. This is what Hussain's factoring talk was about. It was about the idea is everybody does this. Everybody generates large primes and multiplies them together to get N, which is one of the elements of the public key, right? And if you can break N, as we'll very quickly see, you can break the whole system, okay? If you can somehow get a certain, imagine you could get information about the way the lock works on the inside. Imagine you got an X-ray of the lock, right? Then you could probably build a key for it. It's kind of like that, okay? So if you can factor N, the whole system breaks down. And it's a reasonable form of attack. I mean, like Hussain described, it is, I mean, if you don't use a P and Q that are long enough, right? Then you can factor N, right? The longer P and Q are, the harder it is to factor N, right? So you want, ideally, let's say N has been generated securely, right? Then you compute this function. You just multiply P minus 1 and Q minus 1. This is why you don't want to leak P and Q, because if I just give you an N, if I give you 1001, right? I don't know if that's a product of primes, but let's say it is, all right? Can you tell me what the two primes that you multiply to get 1001, if you subtract one from each of them and multiply them, what are you going to get without actually knowing those primes? You can't, right? You actually have to know P and Q to compute that function phi, P minus 1 times Q minus 1. Okay, now what we do is we choose some E, okay? And we'll talk more about E in just a little bit. But you can choose any E that you want with one restriction. It's co-prime to whatever, P minus 1, Q minus 1, and then you find its modular inverse, modulo phi, okay? Why am I being so strict about E being co-prime? Quick, I want an answer for this, like really. I want you to think about why I'm being so strict about the fact that E is co-prime. It's up there in red. Why is it up there in red? The reason is, going back to modular inverses, they only exist if A and M are co-prime, right? So D will only exist if E is co-prime to P minus 1 times Q minus 1, right? So to make sure that D exists, I need E to be co-prime. Other than that, no restrictions on E. We choose E in certain ways that we'll get, that I might mention at the end if you're interested. But for now, you can choose any E that you want, okay? Make sure it's co-prime so that the inverse exists. And this is what forms our public key and this is what forms our private key. Now, these last two slides are what we cover in every intro to crypto meeting. And the problem with these two slides is that it doesn't tell you anything about why it works. If I choose D like this and then do the operations on the previous slide, right? Why is it that, M pops out or C pops out, or, why does this system correspond to the image I had on the board 2 slides ago? It's not obvious, right? It's not at all obvious. So let's make sure that these operations, when we do them all together, we actually get M at the end. Now I want you to go back one slide, Aditya. Thanks. These are the operations we're doing. Look back at them, right? We have N comma E, we take some message M, we raise it to E mod N, and then we raise it to D mod N. So what we're trying to prove, not 2 slides ahead, what we're really trying to prove is that M raised to E raised to D mod N mod PQ is M again. The fact that if you exponentiate it twice like that, you're going to get back the message. How do you know that? Because if we can prove that this is true, then we know that the system works as described. But if we cannot, then it doesn't, right? All right, so let's go on to figuring out why this system works, okay? How do we calculate D? D is E's modular inverse, E is D's modular inverse. That means E and D, if you multiply them together, right, you get 1 mod the totient, mod phi, mod P minus 1 times Q minus 1. But by the definition of, modularity like we described it, remember how we could do that trick with M divides A minus B? That trick is always useful, okay? That means that phi divides ED minus 1, right? Or ED minus 1 is phi times something, right? Therefore, you can write what's up there in red. ED minus 1 is equal to A times some P minus 1, or it's also equal to B times some Q minus 1, right? Convince yourself this is true. Why does this have to be true? M divides A minus B. We looked at that, right? That means phi must divide ED minus 1, right? If phi divides ED minus 1, that means phi times something is equal to ED minus 1, right? If phi times something is ED minus 1, I'm just calling those things differently. In one of those cases, I'm calling it A. In another case, I'm calling it B, right? And I'm making sure that, P minus 1 and Q minus 1 hang around. But these are just different ways to write that product, right? Clear? Any questions about this? No. Okay, next. All right. So remember from the CRT, we said that if we had something like mod P and then we had something mod Q, we could construct a solution mod PQ. Turns out you can go backwards too. So we had that whole expression, right? We had M to the E to the D mod PQ. If we can separately show that M is M to the E to the M to ED, right? Mod P, and separately M is equal to M to ED mod Q. If I can show those two things separately, that's good enough, okay? Here's how we do it, okay? If M is just 0 mod P, that means P divides M, right? If P divides M, P divides any power of M, right? For instance, if, I don't know, 5 divides 25, 5 divides 125, right? So that case is easy. That's the easy case. Here's the hard case. Just look at what's in red, right? M to the ED is M to the ED minus 1 times M. That's the rule of exponents, right? You pull the M out and then you do ED minus 1. We know something about ED minus 1 though, right? We know it's A times P minus 1. That's what we did last time, right? And can you figure out where to go from here? Is there something we covered that tells us what to do when we have something of the form M to the P minus 1 mod P? Spent a lot of time on this. What is M to the P minus 1 mod P? Next slide. Fermat's Little theorem. Anything to the P minus 1 mod P is just 1. We spent a lot of time proving that with necklaces, right? So that thing becomes a 1 and we get out M at the end, right? That's Fermat's Little theorem. And so we've shown that if you do M, raise it to E and then raise it to D, construct it in the way we talked about, then at the end you can pull out M. Now, tell me something. Is there anything special to me sending E or D? Theoretically, don't worry about like actual attacks right now, okay? Imagine you created the system. Is there anything special? So I'm computing two modular inverses, E and D, right? Does it really matter which one I send out to Alice? Does it matter whether I send N comma D or N comma E? Does it change the system? The answer is no, it does not, because they're modular inverses. As long as I do M raised to E times M raised to E and raise that whole thing to D, it's going to be fine, right? It doesn't matter what order you do these things in. The fact that it doesn't matter what order you do these exponentiations in, by the way, is the basis of another crypto system called Diffie-Hellman. In practice, there are certain ways we choose E and D, okay? We choose E to have low Hamming weight. Anyone know what low Hamming weight means? Low Hamming weight means if you write out the number in, well, binary, right? It'll have a lot of zeros in it. It's going to have holes in it, right? That's how I look at it. So which number has lower Hamming weight? It's the one at the bottom, more zeros, right? Why do we choose it like this? Well, in the real world, we use how do you do modular exponentiations? And there's a question that should really bug you right now. If I describe this whole system to you it should really bug you that, well, he said use gigantic numbers for P and Q for it to be secure. How am I going to exponentiate such large numbers? Have you all ever tried doing like big exponentiations on a computer? Computers are not good at big exponentiations, or well, not fast enough, right? And if we have numbers like we were talking about the other day, 2048 bits, can you exponentiate two 2048 bit numbers? The answer is no, because first of all, hardware has support only up to 16 bits right now. And if you're not using like hardware ints, then you're going to be using big int libraries, which are already slower, okay? There is no way you're going to exponentiate two such large numbers. So how do you do it? How does this system even work in the real world if we can exponentiate large numbers? The key insight here is a similar insight to what we did when we did that whole mod 9 thing, okay? The insight kind of is you're taking it mod some other number, right? So before, you don't have to do the whole exponentiation first and then take it mod, right? You can alternate between these, and there's a very clever way to do it called the square and multiply algorithm. And the square and multiply algorithm relies on this binary representation, okay? And the square and multiply algorithm is really simple. It uses powers of 2. What it does is it takes each of these, multiplies it by a power of 2, and then basically processes them like that, taking it mod every time, okay? If you're multiplying, is it better to multiply 1 by a power of 2 or 0 by a power of 2 for processing? If something turns into a 0, it's easier to work with, okay? This is why we use low Hamming weights for E. And the reason we generally want E to be small is because there's a whole class of attacks called Wiener's attacks that can be used on a large E. Note, it is only convention that we call public key E and private key D. You must understand this for you to understand RSA. It doesn't matter. They are just modular inverses of each other. All that's important is that they're co-prime to the totient. Why can't you break this? Because here's what you have as an attacker. Now look at the system as an attacker, okay? What do you see as an attacker? Can we go back to the slide where we had the image, right? You're in the red zone. What do you see? You see n comma e going to Alice, right? And you see basically a locked m raised to e mod n going back, right? How are you going to compute d? Because you want to compute, this is what you want to compute, right? How are you going to get this without, well, what you want to do is find the modular inverse of E, but you want to find it modulo, which is P minus 1 times Q minus 1. But you don't know P and Q, you only know N. So how are you going to invert E? The only way we're going to invert E is by factoring N. And that's why Husnain gave his presentation. That's about it. Any questions about all of the slides? Any questions in general? Open. Or anything, any algorithms, Euclidean algorithm, the mod 9 trick, any of that. If you didn't understand the necklace proof, that's an interesting proof. We can talk about that later. It's kind of subtle, but you know. Yeah. Oh yeah, there are 2 challenges up. The first one is make an RSA implementation in Python. I don't want you to implement the PKCS standard, okay? All I want you to do is implement exactly the operations we talked about, generate n, right? It's an interesting experiment to figure out how do you generate primes themselves, okay? You don't have to do that. There's a function you can get from PyCryptodome called getPrime that'll just give you a prime, right? You can examine that further if you want. It's an interesting exercise. And then that challenge is just write RSA. So it's about like 6 lines of code, and you can DM me your code or show it to me during the meeting for the flag. And the second challenge is you're not allowed to use Python's POW anymore. So Python's POW takes a third argument from modulus, right? You're not allowed to use that. So you have to somehow figure out how to do these gigantic exponentiations, right? Mod something. So I'd recommend using square and multiply. There are definitely other ways to do large exponentiations. And I don't know if we specified in the challenges, but I do want you to use like large numbers, at least use primes that are 256 bits long, right? So that you have to reckon with large exponentiation. Otherwise, it's not fun. Okay. Okay, if there are no more questions, that's enough. Thanks for your time, everybody. This was fun. CS 173.